Hi all, we're just waiting for a few people to attend in person, but we're starting shortly. Thank you. Don't worry about it. Okay. Ready? The community in the chat so they can hear us.
Can everybody hear me?
Yes, but there's a bit of an echo.
Is that better?
Much. Thank you.
Okay, great. Thank you. Okay, so good evening and a warm welcome to all of those who join us both online and in person. This evening, I have the pleasure of introducing Josh Dunlop, an engineering geologist from Jacobs, who will present to us on subsidence in the Mersey Mudstone. Thank you. Take it away.
Brilliant. Thank you very much. Thanks to everyone attending in person and online, and Happy New Year 2023 to everyone. So yeah, as Seb said, this is a talk I'm going to give on the impact of groundwater on the Middlewich Eastern Bypass. It is a rerun of the Gloucester Award talk that I gave in November 2021, which was 15 minutes long, but this is sort of dragged out to 35, 40 minutes. And the project, I've got to say this from the start, is still ongoing. If anyone heard my original Gloucester talk, I did say this at the start of that as well. It's still ongoing. There's still confidentiality restrictions on the information I can disclose, but hopefully it'll be nice and informative and interesting way to kick off CPD for this year. So a bit of an introduction on myself. Grew up in the Isle of Man, then came over to the mainland, as it's called, and then did a geology degree and a engineering geology degree at the University of Leeds. During my bachelor's, did a year of soil engineering geoservices as a contractor, and I've been working at Jacobs ever since graduating the master's. Like I mentioned a second ago, I won the Gloucester Award for this talk in 2021. And as part of the prize package for that, you get the opportunity to sit on the engineering group of the Geological Society committee, of which I've taken over the early careers lead, which I'll speak about right at the end of this presentation. So just for a bit of a starter and an introduction onto sort of what I might talk about this evening, I'll give you a brief history of Middlewich, and it may lead to some clues about the stratigraphy, about what I'm going to be talking about. So the Romans called Middlewich Salinae. According to Collins English Dictionary, the suffix wich refers to a salt-producing town. You can see three of them on the right-hand side there. The four Cheshire witches, so that's Northwich, Leftwich, Middlewich, and Nantwich, are known as the Domesday Witches. These were recorded way back in the Domesday Book in 1086. And 57% of the salt that you use on your fish and chips and cooking is produced by British Salt in Middlewich, commonly under the Saxa brand. So if you didn't know already, I might be talking a little bit about salt and subsidence this evening. So there's a bit of an agenda then. I'll give you a background to the project about Middlewich Eastern Bypass. I'll talk about the ground model and the groundwater regime, including the stratigraphy and potential geohazards. I'll then talk briefly about the groundwater impact, split that into anthropogenic and glacial. I'll then go into a bit more detail about the ground investigation and the strategy and results, which is something I didn't get to talk about on the original talk. And then link back to the future impact of the site, which was the topic of the original glossip, and I'll wrap up with some conclusions. So Middlewich Eastern Bypass is approximately 3 kilometres of new highway, mostly at grade to the south and east of Middlewich Town Centre in Cheshire. However, there will be 2 bridges to the south of the scheme, which will induce some significant loading at the ground surface. The parties, according to CDM, we've got Cheshire East Council as the client, we've got Balfour Beatty and Ringway Jacobs as the principal contractors, and ourselves, Jacobs, as the designer. And like I mentioned right at the start, there is some confidentiality issues and restrictions on what I can say, especially sort of questions at the end, but I'll do my best. But just a bit of a zoom in here then. Hopefully you can see the mouse if I move it over. I have to bring it up. It's all right. There we go. So for a bit of context then, where I've got the mouse currently is the Trent and Mersey Canal, running sort of this direction up the page. So we've got a small bridge from the existing road over the Trent and Mersey Canal, and goes into a bit of a roundabout, and then quite high embankments over the existing Northwich Sandbach freight line. And this is, yeah, so that's the 2 bridges for a bit of context. Left again. So before we went to site and did any investigation, we obviously looked at the freely available data and did a bit of a desk study. And you can see the strat column on the right-hand side is the rocks that we have beneath Middlewich. So we've got the Brooksmill Mudstone, we've got the Wilkersley Halite, the Witch and Biley Mudstones, and the Northwich Halite, which are all members of the Mersey Mudstone group. The Witch and Biley and Northwich are probably a bit too deep to consider at this site, so we've concentrated mostly on the Brooksmill and the Wilkersley. Within them too, we have soluble minerals. We've got anhydrite, gypsum, and obviously quite a significant amount of halite as well. And if we look at the diagram on the left-hand side here, this is the sort of stratigraphy directly beneath where these 2 bridges are. So we've got this area of collapsed strata above wet rockhead, where previous dissolution has occurred, and a residual breccia of the Brooksmill Mudstone now overlies the Wilkersley Halite. Historical boreholes have indicated the depth to wet rock is approximately 60 meters below ground level across the site. And with regard to geohazards, the biggest unknown was the risk of sort of voids, semi-static voids within the halite, especially those that have the potential to migrate to the surface. So in terms of dissolution then, we've got 5 main karstic rocks in the UK, dolomite, limestone, chalk, gypsum and salt. As I mentioned previously, we've got halite, anhydrite and gypsum within our Mersey Mudstone group. So the diagram on the left-hand side, if I scroll across again. So we are in Cheshire, which is this area of Triassic salt and Triassic gypsiferous rocks. And then on the right-hand side of that diagram, it shows an increase in solubility and dissolution rate per strata up the page. So you can see at the top, we've got salt karst as the highest solubility and dissolution rates, and then we've got gypsum second there. So we've got both of those within our stratigraphy. Just to sort of quantify that a little bit, halite has a dissolution rate of 350 grams per litre, which is 2 orders of magnitude higher than gypsum and 3 orders of magnitude higher than limestone, which most of us will know subconsciously, because if you put salt in your sibling's glass at the dinner table, it'll disappear pretty quickly. If you plonked a bit of limestone in, I think you get a whack around the head. So for those who are well behaved, hopefully this embedded video shows you just how quick this can occur. It doesn't seem to be working, does it? What that video would have shown, it's from the BGS. Basically, this white layer would have represented the halite in our ground model, and the strata above, this sort of sandy material, would have represented the Brooksmill Mudstone and glacial deposits. And as you can see, sort of slightly there, the shaded area is fresh water introduced into the system, and eventually the white area, the white salt, dissolves quite quickly, and some videos only 30 seconds long or so. And the strata above, in this case sand, collapses and results in sort of ground deformation and subsidence. left, sorry, yeah. So as a bit of a side, on site, we did our own little experiment. So we got two similar sized lumps of Wilkesy halite core. One was put in a bucket of brine on the left there, and one was put in a bucket of fresh water. So we left it for a few hours and came back. As you can see, the freshwater sample is significantly reduced in size compared to the salt in the rock in brine. We actually think that there was no further dissolution due to the water in the bucket hitting the saturation point. As you can see, this, if you look closely, there's still a couple of sort of orangey red halite crystals within that sample. And it's worth noting as well, something I might come back to you later on, is the colour of the brine now in the right-hand side bucket. It sort of indicates that there's salt and mud clasts that are in suspension, giving it this sort of dark reddy brown hue. So what's our conclusion then doing these sort of experiments and our depth study? Well, this is a rapid process if conditions allow, well within our 120-year design life of the scheme. So that's something obviously we've got to consider. But these aren't the conditions that are directly beneath our site at the moment. Dissolution isn't actively occurring at these rates, obviously, otherwise the towns of Winsford, Middlewich, Nantwich would cease to exist. And they're not all sinking at rates of centimetres per day. So what is the current scenario? Oh, shit. So this figure here is a schematic diagram of what we think the current configuration of the groundwater is beneath Middlewich. If we consider brine has a relative density of 1.2 and freshwater have a relative density of 1, freshwater therefore floats on top of it, kind of like an oil slick in the ocean, despite the horrible comparison. And this interface forms a protective blanket somewhere within the Brooksmill Mudstone. So the diagram there shows that we have this fresh or undersaturated groundwater above, and we have this brine and saturated groundwater below, including in the pore space of any semi-static voids that may be present within the Wilkesy halite. So that's the current conditions. We've got this protective layer, there's going to be no dissolution, easy risk assessment, let's build these bridges. Obviously, that's not quite the case. We have to fully determine the risk posed by dissolution into the future. And sort of the best way to do that is to understand the geological processes that have contributed to previous phases of this dissolution. And these causes of dissolution can be broadly categorized into two categories. We've got regional subsidence associated with major groundwater changes and lowering of that interface. And then we have localized sort of minor groundwater changes, typically associated with human activity. So if we go way back when the Cheshire Basin was a lot further south, we had initial deposition during the Triassic of this. We had influxes of hypersaline water, we had evaporation of the seawater and precipitation of the halite, and then wind-blown mudstones to create our Wilkesy and our Brooksmill mudstones. Some point between then and now, any fresh water in the system may induce dissolution, which manifests as small voids. So in this diagram on the right, I've shown them as voids at the top of the halite and beneath the mudstones. And from a localized dissolution point of view, these small voids may be exasperated and used as preferential pathways for brine that is pumped by humans. And this causes a localized drawdown of the interface nearer pumping stations. And it also means that undersaturated or freshwater even water is pulled through these brine runs. Eventually the strata above, in our case, the Brooksmill Mudstone, can no longer bridge the gap. And there's this upward migration of the void towards the surface, manifesting as surface subsidence in the forms of hollows or brine runs or flashes or meres in the worst case scenario. From a regional context, we have a wide scale or regional scale drawdown of this interface. And this obviously results in widespread dissolution of the halite at wet rockhead. And we have more regional scale collapse of the overlying mudstones and the glacial deposits, depending on the time of collapse. So I'll have a bit more detail on each of these occurrences in the current slides, following slides. So from a localized point of view then, from anthropogenic, the Cheshire Basin has been exploited for centuries, as I said, right at the start. The Romans even called it Salinae, so they knew there was salt beneath the ground around here. Particularly prevalent though was brine extraction from the 1800s to the 1970s, especially sort of wild bastard brining practices in and around Middlewich. And the result and the consequences, therefore, were catastrophic collapse. So on a localized scale, that is the sort of house-sized voids or house-swallowing voids. They can also be sort of palomar-scale flashes along brine runs or meres above flooded mines, typically around the North Bitch area. Sorry, I've just mentioned those flashes and meres. So we just look at a Google Maps image here. So this shows Middlewich and Sandwich to the southeast there. And mouse up again. So if once you get your eye in, you start seeing a lot of these sort of surface features that are now infilled with water. So this area just to the south of Winsford, mouse has disappeared. There it goes. Just to the south of Winsford is called the Bottoms Flash. And that was, I don't know when that was formed, but that is a surface feature likely due to dissolution and voiding and upwards migration. Again, there's another sort of pond there. In terms of brine runs, they're more linear features associated essentially with pumping and dragging of the undersaturated brine and groundwater towards pumping wells. And you can sort of see this one here to the south is in a linear sort of north-south / northeast-southwest trend. And this area to the west of Elworth is also another area that has plenty of surface features that could potentially be due to dissolution and surface deformation. If we look a little bit further north, then we've got Middlewich just in the bottom right-hand corner there. So we've got Winsford and Northwich. And again, once you get your eye in, you can see there's quite a lot of these large bodies of water at the surface, which may or may not have been due to anthropogenic or regional subsidence. Place names also give a bit of a clue to the potential history. So we've got to the very left-hand side there, we've got Hatchmere, Delamere, and then to the very north, we've got Pickmere, and mere is the term basically used for one of these sort of flooded surface bodies of water. So from a regional point of view then, we associate this with the lowering of the interface with a major head of water, typically during a glacial retreat. In Cheshire, this is associated with the major groundwater change during the Pleistocene. So the diagram on the left-hand side there shows the current configuration, roughly what I had in the schematic diagram before. We've got this area of wet rockhead, we've got brine in and around it, and we've got fresh water above, signified by that dotted line. During the Pleistocene, there was a significant freshwater head within the glacier, and this hydraulic imbalance was sufficient to displace that broad interface to depths below wet rockhead. So you can see there above that dotted line, we have all this area of halite that is now prone to freshwater groundwater movements and potential dissolution on a regional scale. And this has resulted in wide-scale collapse of the Brooksmill mudstone above, as all of the strata is now bridging severe voids and collapses into the void space below. And then once the glacier is retreated, the interface rebounds back to something akin to the present day, back on the left-hand side there. So the big question then, knowing what chaos has happened in the past, did we find any evidence of either localized or regional collapse during investigations? What has happened there? Well, first of all, we need to know what we're looking for in our GI. So if we don't know what we're looking for, we're not going to find it. So there's not masses of freely available literature or indeed previous GI case studies. So we went for multiple techniques and a lines of evidence approach for this sort of relative unknown. Starting at desk study, we were looking for any signs of movement from freely available LiDAR data, we were looking at historical maps to see if there was sort of ponds appearing, disappearing on historical maps. And most critically, if any of these are near any of the proposed bridges that go over the canal or the railway. We then phased our GI, scheduled to best determine where to locate our boreholes. They were up to 100 meters depth, so they're not insignificant boreholes. So our first phase was surface geophysics, which I'll talk about in just a second. And the surface geophysics therefore informed our deep intrusive and downhole geophysics. And then phase 3, we had shallow intrusive GI, which was more catering for the rest of the scheme, sort of at grade and small embankments, but also used to sort of ground truth some other areas of the geophysics that we didn't target with the deep intrusive GI. And like I say, that each phase informed the subsequent phases to the best value for the client. So we used 3 different methods of surface geophysics. So this diagram here, the yellow box shows the area of microgravity survey that we've undertaken. This is just for the railway bridge, but we also do this for the canal and a potential subsidence feature further to the north of this site as well. And then all those multicolored straight lines are the survey lines for ERT, which is electroresistivity tomography. We then did surface seismic surveys as well. And you'll see that the 2 lines to the north of the railway are pretty similar to some of the lines in the ERT, and likewise the one south of the railway is also in a similar alignment to the ERT lines as well. And that was just to sort of compare directly. And it was more the critical locations where the abutments are going to be. And then we did some intrusive GI as well. Just on the right-hand side there, I've cut it off slightly, but it's DB01, deep borehole 01, which is off the alignment, and I'll talk about that in a second. And then we've got DB02, DB03, which are on ERT lines, seismic lines, and beneath the bridge abutments, just so we can correlate with this lines of evidence approach, see if there is any potential voiding beneath our alignment. So we think that sort of localized subsidence and region subsidence will manifest themselves in different ways with each technique. At this point, it was a real unknown. We didn't know how they were going to look on our surface geophysics or in our intrusive boreholes. So we needed good ground coverage to detect these changes at the ground surface and spot these localized differences. From a regional scale perspective, we thought this would probably be best with rock core samples. Brecciation will be evident if we get good recovery, and the seismic data might point to any breaks in the halite. So one key area of interest was this pond that was present and then disappeared on historical maps. And it's located 50 meters east of the approach embankment. Like I said there, DB01 was slightly off alignment, but there was this potential pond that we had no idea where it disappeared to. So going all the way back to 1914 on the historical maps, this is the area of the pond. Just for context, that line going sort of northwest, southeast on the page is the same railway line. So our alignment goes to the left of this pond, and we then jump forward to 1961. The railway line's still there. You can see the salt works close by, the canal on the bottom left, and that pond is still shown on this map. Jump forward 6 years, again, more detailed map, railway still there, the salt works there to the top left, and the pond still on the diagrams. I don't know why there's a massive gap. There's about 40 years gap in our fire check there between the 60s and 2006. But as you can see, pretty much everything's still the same, apart from this pond has curiously gone missing where I put that star. And we had no idea why. You can see there's another pond sort of just to the sort of left-hand side and a little bit below. And that's present on all the other maps, and it's present on site, you'll see from the aerial imagery as well. And then from the aerial images, there's that pond I was talking about, just to the sort of southwest. The Trent Mersey canal's there, the existing road's there, and the railway's still there. But there's absolutely no evidence of a pond in this field. So that was a curiosity. our GI evidence found evidence, our GI found evidence of both localized and regional subsidence. So our non-intrusive investigation was best shown, localized subsidence was best shown on our non-intrusive investigation results. So that pond I was telling you about that disappeared, here it is, here is evidence for it. This is our microgravity survey to the northeast of the railway, that's that brown line in the bottom corner. And that is shown as this sort of residual blue area of negative gravity anomaly in comparison to the sort of yellows, greens, reds of the surrounding area. We then did the surface seismic, which is down line 2, as you can see on the left-hand side of that microgravity one, and the pond and the area of negative residual gravity anomaly is approximately change 100, which is shown on this refraction survey as this shallow zone of low velocity. And along the same seismic line, we've probably got the clearest evidence here of localized subsidence. So this is our reflection survey data, and it shows the area of the pond, again, change 100, that we've got these sort of scattered reflections directly below change 100. We've got this potential fault, which is the black dotted line there, just to the right side. And we've got this sort of break in the clear halite reflector at approximately 60 meters below ground level, which is indicated by that yellow line. Just as a bit of an aside, we actually obviously did borehole 1 down through the middle of this, and it was a infilled pond, 2.5 meters depth. So for whatever reason, the farmer has just thrown all sorts of material in there just to level out the field. I imagine it makes it a bit easier to plough, to be fair. In terms of regional subsidence, then, our intrusive investigation was the best evidence for this, and there was widespread evidence, especially of brecciation in the Brooks Mill mudstone. So the picture on the right-hand side there is from core, somewhere between 10 and 60 meters below ground level. As you can see, there's a mix of class-supported and matrix-supported breccia. These are sort of anywhere from millimeter to tens of centimeter scale clasts. And there's a clear difference in colour as well between the browns and the sort of weathered blue mudstone associated with groundwater flows. We also had secondary precipitation of halite and gypsum. You can see in the core photographs on the left-hand side there. In the top core box, we've got these sort of thin fractures that are infilled with gypsum. And in the middle box down there, we've got this secondary precipitation of the Wilkersley. Now, the reason we think it's secondary rather than sort of primary precipitation is due to the colour. Further down, unfortunately, I haven't got a photograph of it, but further down in this core box, we had sort of translucent pink halite, which you normally associate with your rock salts, you know, the Himalayan rock salts that people buy in shops and stuff like that. But further up at this core section here, so this is 88 meters below ground level, we have this quite large fracture, 2 large fractures, and the colour suggests that it is actually halite that has been dissolved, transported and precipitated with the silty, muddy clasts, as was shown in our site experiment, to give it this sort of darker red colour. Fortunately, though, the underlying sort of main part of this GI showed that between the intrusive and the non-intrusive, there was no evidence of pre-existing voids. Well, not bridge swallowing pre-existing voids anyway. But how did we come to that conclusion? So, like I said at the start, it was a bit of an unknown for us in terms of the risk. So how did we assess this void risk? To be conservative, we assumed any zones of core loss exceeding 50 centimeters had the potential to cause significant ground subsidence, or at least ground deformation. So we had to use all our lines of evidence to determine whether these zones of core loss were potential voids or whether they were a result of drilling disturbance instead. So I'll run you through a few of the methods then on the right-hand side. So we started off with our microgravity. Again, this is the same borehole DB01 in the microgravity anomaly. And you can see there, it's plotted right down the middle of this residual negative anomaly in the middle of the microgravity. So then we go along to the third image along, and this is downhole geophysics. And it's a sonar cavity scan at the depth around this zone of core loss that was recorded. I can't remember how big this core loss was off the top of my head, probably about 60 to 80 centimeters. this particular one. So as you can see, the borehole scan indicates that it's fairly normal borehole diameter in the top left. It becomes a bit more disturbed in the top right, and then that black box indicates that this sort of northern wall, as we look at it, it's highly scattered and it's very irregular. So there was the potential that the borehole had sort of gone right down through the middle of a semi-static void. And then the next little picture after that is directly below that. So the borehole's back to a fairly normal diameter. On the very right-hand side at the top, we've got more downhole geophysics, and this area of disturbance and this zone of core loss is shown probably halfway down that, where there's sort of weird disturbance in the logs. Again, don't want to repeat myself too much, but the seismics show that there's scattered reflections. There's not a great reflection on the halite bed compared to the rest of the site. And our refraction survey shows sort of these results as well. Interestingly, if we'd just done ERT surveys, I don't think I would have picked this up as a hazard. The DBO1 is shown there at the far left-hand side of the survey lines that intersected this area of core loss, and there's no real discernible differences from what I can tell. These are sort of, for scale, I think they're down to 30 meters penetration. It's not quite clear. So I don't know, maybe you can interpret it differently to me, but if we just done ERT and had this zone of core loss, I maybe wouldn't have been so confident that it was sort of localized subsidence. And then we also looked at sort of drillers logs. We looked for flush returns. We looked for, so in this case, we had 95% flush returns at the zone that this was recorded. And we also did downhole caliper logging and looked for any signs of sort of recent, in inverted commas, collapse in the core box photographs as well. So we had these multiple lines of evidence at our disposal. I should say, sorry, before we carry on to this slide, again, I can't actually disclose the risk to this site and this project. It's currently confidential in terms of void risk, unfortunately, but that gives you an idea of our sort of process as to how we assess the risk. So for a bit of a recap then, and I'll link back to the title of the original talk. Regional dissolution has developed this collapse breccia. So groundwater has had this major impact on the geology of the scheme. It's shaped the topography, as we've seen with all the surface water features. It's been a catalyst for widespread and localized subsidence in cases. And it's obviously developed this collapse breccia, which itself has brought geotechnical headaches. Sometimes it behaves as a soil, like a residual soil. Sometimes it behaves as a competent rock, and sometimes it doesn't know what it's doing. So yeah, anthropogenically induced dissolution has obviously developed local dissolution features as well. So we have a pretty good idea on the history of the site, but the theme for the original submission was the impact of groundwater, including extreme weather and climate change. So for the sake of continuity, I'll also mention that aspect again, go into a bit more detail about the potential future impacts to the scheme. So if we use James Hutton's principle of uniformitarianism, the present is key to the past, and in our case, the future. We understand the geological processes now that have led to historical subsidence. That's primarily the alteration of the protective brine blanket. So with that in mind, can we predict any changes that are likely to alter the depth of this brine interface into the future, or definitely within the design life of the scheme, and particularly the bridges? And are there any signs of anything that may bring about localized dissolution? For example, is there any semi-static voids that have the potential to migrate to the surface? And how can we address these in design? Well, in terms of design, our best action is to control the drainage. This picture here is taken from Cooper, Farrant and Price, which shows sort of good practice and poor practice. So we've worked quite closely with our drainage team at Jacobs to sort of develop some mitigations for this. So all of our SUDS ponds, our sustainable urban drainage systems, have to be lined, so as to reduce the freshwater pathways to soluble strata. There's under no circumstances any sort of soakaways on site, and all the boreholes that penetrated into the Wilkersley were backfilled without putting any groundwater installations in, just to sort of reduce easy pathways for fresh water and particularly surface water to penetrate down to this soluble strata. However, there is unknown climatic changes. Obviously, we're in a period of dynamic climate change at the moment, and there is potential for increased severe flooding, increased surface water, and this may therefore lead to increased freshwater infiltration and a change in the groundwater interface there as well. That's something we can't really sort of design against. We've added extra factors of safety to our drainage designs in terms of the capacity of all of our urban drainage is sort of accounts for climate change with an extra 3 or 4% capacity for a 1 in 1,000-year event, 1 in 100-year event, sorry. But we've explained to the client and they understand that there is this latent background risk of developing above soluble strata. So just a bit of a summary then. So the impact of groundwater has been profound at our Middlewich site. The changes to the groundwater regime have led to dissolution of the Wilkesley halite, and this dissolution has led to the upwards collapse in the overlying Brooks Mill mudstone. And our ground investigation broadly agrees with this hypothesis. We have examples of localized substance and we have evidence of regional substance as well. And there is always this latent background risk associated with soluble strata. This photograph is on the right-hand side, was taken next to the Trent Mersey Canal, just on the other side of the seismic truck here. So this is the seismic truck we used for the surveys, and that ominous grey building in the background is British salt, where 57% of your salt for cooking comes from. So just conclusions then. The groundwater has a profound impact on the surface geomorphology and the subsurface characteristics of the stratigraphy beneath our Middlewich site. And understanding the geological and groundwater processes that have induced dissolution so far is fundamental in assessing our future risk of subsidence at Middlewich. Just quickly, before I finish and wrap up, as I mentioned at the start, I'm part of the engineering group of the Geological Society. So I'm also now the early career lead and a member of the early careers subcommittee, and you can see on the right hand side how that sort of fits into the main committee. We are currently asking for volunteers to fill the vacancies on the subcommittee. It had a bit of a hiatus during COVID, but I've been tasked with sort of ramping it back up again. So far, sort of 4 people have expressed interest in the roles, which are down at the bottom there. So we've got chair, vice chair, treasurer, secretary, academic liaison, events publicity, and training and CPD. If anyone is interested or wants any more information, feel free to speak to me afterwards or contact me via that email address on screen. But that's me. So if there's any questions, please shout up.
Unmute themselves.
I have a question. You may not be able to answer it. What did you actually find on the Mudstone?